Hello friends, welcome back to our channel. Today we are going to discuss about inert pair effect. So what is meaning of inert? What is the meaning of inert? Inert in the sense, first you see inert. See here the electrons which is not involving in bond formation. Which is not involving in bond formation is calling inert, right? And the pair, you know. What is the meaning of pair? Pair, it denotes always 2, right? No? Denotes 2. So, the 2 electrons which is not involving in the bond formation, that only we are calling inert pair effect. This especially in case of NS electrons will happens. NS electrons, it will happens. When you are considering p block elements you take, like group 13 p block elements you take, group 13, 14, 15 and 16. This 16 only. And till 17 consider just NS2 NP1 is the outermost configuration for 13, NS2 NP2 for 14, NS2 NP3 for 15, NS2 NP4 for 16, NS2 NP5 for 17. Okay, so we can negligible this. I am not going to explain about group 17 now because they are halogens. Okay, so we will discuss about the from boron family to oxygen family. Okay, so now the higher oxidation states you take here, like 2 plus 1 3. So the maximum oxidation number forms by the third A group elements, that is 3. And the fourth A group elements, that is the 14th group, that is a plus 4. And fifth A group elements, plus 5 and plus 6 is the maximum oxidation numbers is able to form by the P block elements, these 13 to 17. Okay, and P block elements exhibit variable oxidation states also. These variable oxidation states, P block elements, maximum oxidation state is not shown when it is coming to the down the group. So down the group you take, for example, boron, aluminium, gallium, indium, thallium you take here. Okay, so atomic number 5, 13, 31 and then 49 and 81. So when you are coming to these atomic numbers, what will happen here? It is coming down the group. In case of down the group, the oxidation number will be decreases, like nearly 2 units, plus 2 units is less than the normal oxidation state. Okay, plus 2 units will be less than the normal oxidation state. And one more thing we can say here, always the less oxidation state or less oxidation number will be high stable, less oxidation number high stable, and more oxidation number will be less stable. So this one you should remember. In case of 13, this is 13th group element. When you are considering to the 14th group element, like here, one more important one I will say here, one thing I will mention, heavier post-transition elements. Heavier post-transition elements. Usually transition elements means D block elements, right? So D block elements are present in which periods? 4th and 5th periods, right? No? So 4th period you consider. 4th period, scandium to zinc. Okay, scandium to zinc. Zinc atomic number 30 and here 21. So when you are coming to this afterwards, what is the element? 31. That is gallium. But gallium comes under which block? P block element, right? And then 5th period when you are considering, next in 5th period, indium it will come. 49 atomic number, right? 49. So this also will come in P block. And 6th period you take. 6th period, thallium it will come. So atomic number is 18. So when it is coming to the 4th, 5th and 6th periods, these elements are located like 13th group elements, 14th and 15th, 16th and 16th elements are located in the 4th, 5th and 6th periods. So that is the reason these elements we are calling heavier. Heavier in the sense they are high, right? They have a high atomic number. High atomic number. And then post means after the transition elements they are coming. After the transition elements, these elements are coming. That is the reason we are calling these elements are heavier post transition elements. And these are located in the middle of the transition elements, and then after middle of the transition elements, and after that metalloids also will be there here. Metalloids. I will show you periodic table. Okay. So in that, so here you see when you are seeing the periodic table, see like atomic number 31 here, 21 to 30. So here what will happen, sir? See here, zinc, gallium, next indium, thallium, next here again tin, lead, even bismuth. So here the color one, no, brown color one, the orange color one, it shows metalloids, all these one. Okay, until here it's a D block elements. So these elements are located in the middle of the metalloids and the transition elements. That is the reason these are placed in the middle, and they have variable oxidation states also. And here when you are considering, like you see third year group elements you see, especially third year group element, we can give one shortcut as a Bal Ganesian Thailand. Like my remembering, I remember like that. You can remember your own convenience. Third year group elements, thallium you take. +1 oxidation state is more stable than the +3 oxidation state due to the inert pair effect. Inert pair and reluctance of NS electrons, that I will show you. Fourth year group elements, lead. +2 oxidation state will be more stable than the +4 oxidation state. And when it is coming to the 5th year group elements, bismuth, +3 oxidation state is more stable than the +5 oxidation state. So these we should remember definitely. You should not forget about this. And then just I will show you with electronic configuration. Just you see here. See, boron atomic number 5. So I am writing with the helium shortcut form. So helium 2 atomic number. So 2s2 2p1. When you are taking aluminum 13. So neon inert gas 10. Okay. And then 3s2 3p1. So 10 plus 3 13. Next when you are considering gallium you take 31. 31 in the sense argon we can take. And here 3d electrons will come. So 3d10, argon 18 plus 10 28. And again the next shell 4s2 4p1. Next you take indium. Indium atomic number 49. So we can say here krypton 36 atomic number. Next fourth shell will come 4d10 and 5s2 5p1. You take the next one is thallium, higher atomic size. This is less stable will be there. And here xenon 54. Next here 4f orbitals also will involve, and then 5d orbitals also will involve. 5t10. Next sixth shell is the Valency shell 6s2 6p1. So when you are considering here all the configurations, you take here 4s2 5s2 6s2. Actually the 6th p, these are the valence electron, and these electrons like ns2 electrons, these ns2 electrons are not able to involve in the bond formation. Means here what is happening, like in heavier post transition elements, the outer electrons, that is ns electrons, have a tendency to remain inert and show reluctance. Reluctance means unwilling to take the part in bond formation. That is the reason, due to these all reasons, we are having some elements, especially in the p block 4th, 5th, 6th periods, some elements will have the 2 oxidation states also. The higher energy will be less stable and the less oxidation state will be more stable. Okay. And then see here, even though here I'll show you, like see, this is number of protons and first shell, second, third, fourth and fifth. Okay. So you consider this is a valency shell. This is valency shell. Nth shell in the sense this is n-1, right? So this is n-1. So what will happen here? Here the electron will be there. This is valence electron, will imagine. So this electron is trying to come towards the nucleus to attract about the protons. But the remaining electrons are here, no? Here are there, here are there, here are there, many are there, no? So these all are not allowing this electron to come inside the nucleus to attract about the protons. Okay. So what we will call this as a shielding effect. Here shielding effect is happening. So, but here even though s electrons are there here, but s electrons are not able to involve, and especially in the case of thallium you consider. Here 4 f electrons, 14 completely filled are there and d electrons also completely filled, right? No? D electrons will be 10 capacity and f will be 14. So these 2 electrons also completely filled here. So there is no involvement of s orbital electrons in the bond formation. That is the reason we are calling this is inert pair effect. I hope everyone understood about this video. Thank you all.